Okay. So this is my GitHub notebook, GitHub, and I'm opening my Python notebook in Google Colab, which is associated with my Gmail account. Fine. Huh? So all these parts are completed yesterday. Now what I'm trying to work on it, this one, ANN without hidden layer, but with nonlinear activation function. Which activation function I'm using? Sigmoid activation function, and I'm using the bias parameter also. That's what we discussed in the yesterday's class. This flowchart I'm trying to implement. So this flowchart is the algorithm which is used to train the ANN model, which have only input layer and output layer without hidden layer and with nonlinear activation function that is called as the sigmoid activation function. Now we are trying to implement it. Okay, I will explain one by one implementation part by seeing this flowchart directly. Fine. Now move to the implementation part. Okay. So first I am trying to connect my Google Colab with my Google Drive where my data is available. And the data that I considered here is maybe I forgot to mention data is available. Yeah, maybe in desktop it is available. Sample data. Yeah, this one. So this is my data set. This is my data set where A, B, C are called as the input features, where X is called as my target variable. That means I am trying to predict the X values based on the A, B, C values. So this is my data set. This data set is already available in my Google Drive. Okay. So that's why I'm trying to connect my Google Colab with my Google Drive so that I can access this data file from my Google Drive. Okay. So to connect my Google Colab, with Google Drive, they simply run this mount code from google.colab, import your drive, and drive.mount, you have to connect your drive. So simply run this cell. Only these 2 lines of code is sufficient to connect your Google Colab with your Google Drive, where your data is available. Okay. I hope you understand. So whenever you are working with the Google Colab, it is better to connect your Google Colab with your Google Drive, where your data is available. Okay. Now I'm trying to connect my Google Drive with my Gmail account. Done. So now I'm connecting my Google Drive with my, see if you observe here, nothing is available as of now. But once the drive is connected, all the information that is available in my Google Drive will be visible here. Done. So you can refresh. See, this is my drive. And this is my Google Drive. In the Google Drive, in the NNN data, and you are able to see a sample data. This one, sample data sigmoid. This is the data file I want to use for this activity to train for the ANN model without hidden layer, with the output layer, with the sigmoid activation function. Okay. So if you want to read this Excel data into the Google Colab, now you need these 2 libraries. One is the pandas library for the data manipulation, numpy library for the arrays operations. Simply run this cell, import pandas library and also import the numpy library. Now I want to read the data which is available in this Excel file. How you can use pd, there is a pandas dot read Excel command. Read underscore Excel will nothing but the read the Excel data. So read underscore Excel, and within the double quotes, you have to pass your path where the Excel file is located. So you can see this is the sample underscore data underscore sigmoid. You can see the 3 dots. Click here. Simply click on copy path, and that path you have to paste here. So once you paste this complete path, then what it will happen once you are executing this cell is it will read the data available in this Excel sheet and stored with a variable called data. Okay, whatever the information is available in this Excel sheet, that will be read and that will be stored in a variable called data variable. So simply click here and visualize the data what is available in the Excel sheet. So this is the my top 5 rows I am able to access. So they are 0.1, 0.2, 0.3, corresponding output values are 0.96. So I'm trying to predict the X value based on the ABC values. See, dear participants, approach will be remain same. Here I am using some random data. If you are working on the temperature prediction, you can use your temperature data. If you are working on the humidity prediction, use your humidity data. Or if you are working in some other problem, you have to collect the data related to your problem and load it. That's it. Only numbers, right? That's what I'm doing here. Okay. So this is the, just I have the data which I want to use to train my ANN model. So what will be the, our next step? Once we imported the data, so our next step is split the data. You have to split the whole data for the training purpose and also for the testing purpose. Yesterday I said, whenever we are train the students, if we have a 20 questions with us, if we have a 20 questions with us, out of 20, maybe 15 or 18 questions only demonstrated in the classroom, and 5 more questions we kept aside that we will use for the testing during the examination to test the knowledge of the student. In the same way, whatever the data we have to use the some part of data for the training purpose, for the train the neural network model, and we have to keep the remaining data for the testing purpose to test your model. I hope you understand up to here. So that is called the data split. Now I am trying to use the data split. So if you want to split the data, sklearn is the machine learning library available in the Python. From sklearn.model selection, you have to import a method called train underscore test underscore split. This train underscore test underscore split method will split the data row wise randomly for the training purpose and also for the testing purpose. Listen all my sentences what I am using, because these are important to write the quiz examinations. Already based on the yesterday's content, already I created the 2 quiz examinations in the canvas and already created the 3 programming assignments based on the day 1. So total 5 are available for 50 marks in the canvas. Try to attempt on or before 6 December 6th. So coming to this train test split method will be used to split the data for the training purpose and also for the testing purpose. So this train underscore test underscore split method will split the data row wise randomly for the training and testing. So you have to import that train underscore test underscore split method. Now for this method, for this function, you have to pass the data which you want to split. You have to pass the data which you want to split. And you have to give test size. Test size is nothing but the how much percentage of data you want to keep it for the testing purpose, and remaining data will be going for the training purpose. Here 0.05 means 5% of data is used for the 5% of data is used for the testing, and remaining 95% of data will be used for the training purpose. So now this train underscore test split method will split the data for the training and testing. Whatever the data that will be for the training will be stored with the data underscore train. Whatever may be the data for the testing, that will be stored under the data underscore test. So what I mean to say is data underscore train has the training data, data underscore test has the test data. And these parts are only for my latter part only. So Q1 is nothing but the number of samples in a training data. Q2 is nothing but the number of samples in the test data. Q1, that is the length command I am using. So Q1 is nothing but the number of samples in the training data. Q2 is nothing but the number of samples in the test data. Okay, fine. So this is only to convert my data train and data test into the array format. Now you can run this cell to split the data. So you have the total data of 6 or 7 samples, I think. Yeah, I have total 7 samples. So out of 7 samples, maybe 1 sample is going to the testing and remaining 6 samples are going to the training purpose. Okay. So once that data split was completed, next step is, what the next step? That means we are reading the data. So we are reading the data. So after reading the data, what the next step? We are reading the data A, B, C, and X. And we have to randomly initialize the weights and bias parameters. We are randomly initializing the, so JM, you are any doubt, please? So you raise the hand. If you have any questions, please. I think Mohan something, JM. If you have any questions, please. Jatavat Mohan. Okay, fine, no issue. So if you have any questions, you can unmute yourself, you can ask a question or use the chat box also, no problem. So now coming to, so randomly initialize the weights and the bias parameters. So what we have to do here, randomly initialize the weights and bias parameters. So this is the part. So weights, nothing but the W matrix, weight matrix, bias, nothing but the bias matrix. So random initialize, to random initialize, we have to use np dot random dot uniform for randomly generate the values to random initialize the weights and the bias parameters. So this is we have to use. And you have to give the range. So I want to initialize the weights and bias parameters randomly. Okay, but what is the range? On what range you can choose the, you can pick the values randomly. So I am choosing the lower value -10, the upper value +10. You can choose any range, -100 to +100, -1000 to +1000, that's your choice. So whatever the range you mentioned, lower limit and upper limit, between that values, it will generate the random numbers. Okay. And here size is 3, 1, and here size is 1, 1. So yesterday I asked the same question and no one is responded. Again, I answered that question also. Again, I'm asking, may I know why it is a 3, 1 and why it is a 1, 1? Anyone, please? So if it is a active, then it will be more interesting for you and for me also. Why I am choosing the size is a 3, 1 and why I'm choosing the size is a 1, 1 here? If you are participating actively, that is more interesting for you and for me also. If you not understand, please let me know. I will explain once again. That's also not a problem. So why size here 3, 1 I am choosing? Why size is 1, 1 I am choosing? To train my ANN mod with a sigmoid activation function.
Okay, anyway, you have three weights is required. We have because we have three parameters.
Sir,
ABC.
sir.
Hello, am I audible?
Sir.
Am I audible? Hello.
Yes, yes, sir. Like you can increase voice.
Okay, 1 minute.
Sir, please, sir. So I am asking why we consider 3, 1 here and why consider 1, 1 here while initializing the weights and the bias parameters.
Hello, sir.
Sir.
Am I audible?
Yes, sir. Yes, sir. Clear, sir. Now.
Yeah, sir. Because we have three parameters ABC, so we need three weights. So 3, 1.
Right, sir.
Three
So
rows and one column. So then
right.
bias is one, only one is there.
Right, sir. Right, sir. So come back to our architecture. We have the 3 input features. So we have the 3 weights, and there is only one bias parameter. That's why for the weights we are taking the 3, 1, 3 rows and 1 column, and bias is the only one element. So 1 row, 1 column. That's it. So that's the reason we consider the 3 and 1. Based on your requirement, you have to change this size. That's it. So based on your requirement, you have to change the size. Okay. Maybe this type of questions I asked in the quiz examinations also. So I asked one question, that is, I'm trying to predict the temperature on a particular time based on the last 4 hours temperature data and also based on the last 4 days temperature data, but at the time of the prediction. What I want to tell you is, if I want to predict the temperature in SR University at 2 o'clock, I want to take the last 4 hours temperature data. Let's assume 1 o'clock, 12 o'clock, 11 o'clock, and 10 o'clock. At the same time, last 4 days data. That means what will be the yesterday 2 o'clock temperature, day before yesterday 2 o'clock temperature, and before that one and before that one. If that is my problem statement, and if you are designing an ANN without hidden layer, without any hidden layers, my question is how many weights are there? How many weight parameters will be there in that ANN model? Anyone? So one of the question in the quiz examination, I want to design an ANN model without hidden layers to predict the temperature at 2 o'clock at a particular time based on the last 4 hours temperature. That means 1 o'clock, 12 o'clock, 10 o'clock, and 11 o'clock temperature. And also last 4 days. That means yesterday 2 o'clock, day before yesterday 2 o'clock, and that before 2 o'clock, and that before day 2 o'clock. if you are designing the ANN model like this, then how many number of weight parameters will be? That is one of the question in the physics examination. Anyone able to answer?
Is that 8?
Right, sir. It is the 8. So because we have the 8 input features, you have the 8 weights. So like that, based on your problem requirement, the values will be changes. So you have to understand the code. Then you can do the small modifications in that codes. So now as of now, we have the only 3 input features. So it's the 3, 1. So weights are initialized. These are the random weights. And this is my random bias parameter. These are my random weights. And this is my random bias parameter, randomly initialized. So after that, what is the next step? Go to our flow chart. Go to our flow chart. Then you can see our thing. So after that, what you have to do? Eta value, assume 0.1, and number of epochs, something, maximum number of epochs you want to tell, you have to give that epochs. So eta L value, nothing but eta value, that is called as the 0.1 learning rate. Epochs equal to, I am considering the 10,000 epochs because it's a computer. So we can give any. So sorry, 10 epochs I will write epochs. So epochs nothing but the maximum number of iterations you want to write. Fine. After doing these two, now see, you are able to see the 2 for loops here. 2 for loops, right? So again, one more question in the physics examination also, like how many for loops are there in a Python program when you are writing to train the ANN model? So there is a 2 for loops, inner for loop for the sample, outer for loop for the iterations. So there are 2 for loops. So for I in range of epochs, iterations, for epochs. Okay. You see epoch, right? So I have to do the same EPOCH epoch. Right. And J in range Q1. Why I am taking the Q1, not Q2? Any idea? Why I am taking the Q1 here, not Q2? Because we have the Q1 here and Q2 here, but I am taking the Q1. What is the reason? Reason is, so this is the training algorithm. So to train the model, we have to use the training data. So training data is nothing but the Q1. This is the training data, number of samples in a training data represented by Q1. That's the reason why I am using the Q1 value. Now see inside, now we have to calculate the Z value, nothing but the input. Z equal to weight into your input features plus bias parameter. That's what I'm doing here. The matrix multiplication. Weight into input features plus B is a matrix multiplication. Z equal to NP dot dot. There's a matrix multiplication between data underscore train. That's the training data of a particular sample, 1 or 2 or 3, whatever it may be for that sample. You have to take the first 3 columns. Why only first 3 columns? Because if you see this data, the first 3 columns are the features, input features. So here we have to take the input features, right? Here A, B, C are called the input features. You have to multiply the weights with input features. That's why I'm taking the input features from the training data and multiply with the weights. Now it's the matrix multiplication, and whatever you are getting, you have to add the bias parameter. So this is called as your input to your output layer, right? If you are not using the segment activation function, if you are using the linear activation function, whatever the input is there, that will be the output for your ANN model. If you are using the linear activation function, whatever will be the input to your, whatever may be the input to your output layer, that will be the your output also. If you are using the linear activation function, but if you are using the sigmoid activation function, whatever the input is given, but the output will be 1 by 1 plus e power minus z, where z is the input. Because I am using the sigmoid activation function. So my output y equal to 1 divided by 1 plus e power minus x, nothing but e power minus z. How we find the exponential of minus z in the Python? That is based on the NumPy library, np dot exponential of minus z. So this is the segment activation function. Yesterday we discussed this one. See, f of z equal to 1 by 1 plus e power minus z for the segment activation function. So that it is a y equal to 1 by 1 plus np dot exponential of minus z. So this is the output of your ANN model. So after that, what's the next step? You can go to our flow chart. As per our flow chart, after you are calculating the z value, after calculating the o value, after calculating the z value, after calculating the o value, now calculate the delta W and delta B. How we calculate the delta W? Eta, learning rate, desired value minus actual value, sorry, predicted value. Sorry, I got one call. Sorry. So now we are going to calculate the delta W and delta B. Delta W and delta B, right? So how we calculate the delta W? This thing already we derived. That's why I'm not explaining again. Eta, learning rate, into desired value or actual value that is coming from the data set, minus O, that is the predicted value by your neural network model, and O into 1 minus O and your inputs. That's what I am doing in the code also. Delta W or DW equal to L, learning rate, eta. Desired value, where the desired value is available, actual value from the data set is available. Actual value will be in which column? Either 0th index column, index 1 column, index 2 column, index 3 column. So I'm taking the 3 here because in the training data, index 3 column, nothing but the 4th column is my desired output minus my prediction O into my prediction into 1 minus O. This is as per formula only, as per our formula only, right? And multiplied by data underscore train. What we are going to multiply with our input features, right? Our input features are like a 0.1, 0.2 and 0.3, but it is like a row matrix. But we require the A, B, C as a column matrix. So for that purpose, I am taking the transpose of that input features. Dot T, that is called transpose. So transpose of that matrix. It will give the DW. Once you got the DW, later calculate the DB also. Delta B equal to eta into D minus O into 1 minus O. This is the eta, nothing but learning rate, into my desired output minus predicted output into 1 minus predicted output. Okay. Now you have to, once you calculate the delta W and delta B, now update your weights. Weights equal to weights plus delta W, bias equal to bias plus delta B. Right? So this process will be repeated. How many number of epochs you mentioned? How many number of epochs you mentioned? So someone, can you confirm as of now? Let's assume I want to print Q1 first. I want to print Q1. So what is the Q1 value? I'm getting the Q1 value equal to 6, right? Now my question is, if you run this algorithm, if you run this code, how many times bias parameter will be updated? That's my question. How many times my bias parameter will be updated in the complete training process? This is also one of this type of question also available in the physics examination. So that's what I'm asking. How many times your bias parameter will be updated in this training process? Anyone, please? Question is how many times bias parameter will be updated? We know that Q1 equal to 6 here. Anyone, please? How many number of times this bias parameter will be updated here? No idea. So this is the epochs into Q1. So this is the 10,000 epochs and Q1 equal to 6, that means 60,000 times this bias parameter will be updated. Now I am trying to run this code to train my model for the 10,000 epochs. That's it. So training was completed. Okay. So initial my weights and bias values are these, and after training, this is what's updated. So this is the initial values. These are the updated values. Once the training was completed, our next step is we are trying to observe the performance of my ANN model. How we observe the performance of the ANN model? Based on the training error and testing error. If you want to find the training error, first you have to calculate the predictions on the training data and compare your predictions with your actual output. Then you will get the error. Similarly, if you want to calculate the testing error, first calculate the predictions on the testing data and compare your predictions with the actual test day output and calculate the error. If these errors are within the limits, these are the very less values. If you and your client are also happy, then you can directly deploy your model. So deploy your model is nothing but the use your updated weights and the bias parameters in the back end of your application. That's it. So now I want to do the predictions on the test data. So this is the predictions code test with the zeros I initialize, right? So now I am taking the every sample from the test data and calculate the input to your output neuron. That is called as the matrix multiplication of your weights and the input features, add the bias value. Now O equal to 1 by 1 plus exponential, np dot exponential, because I'm using the sigmoid activation function. So that is the actual output value. Previously, if you're using the linear activation function, your Z itself is the output O. But here we are using the sigmoid activation function. So your O will be 1 by 1 plus e power minus Z. Now, whatever the output you are predicting, that will be stored in this variable as an array. Okay. Now I am running this cell and I'm getting the output value 0.6145 something on the test data. Now, if you want to calculate the test error, so for a mean squared error function or method, you have to pass the actual output and also predicted output, then it will calculate the mean square error. So how the mean square error will be calculated? So the mean square error value will be 0.00025, almost equal to 0. So I am happy with the error. And also I'm trying to calculate the error in the training data. So training data means again you take the training samples Q1. Now calculate the input to your output layer, nothing but the weights into features plus bias parameter. Whatever the input you are getting to the output layer, calculate the output of your output layer, that is called the 1 by 1 plus e power minus Z, and that output is stored in the print underscore train. So these are the predictions with the training data. So these are the predictions with the training data. Now calculate the training error. If you want to calculate the training error, for a mean squared error, you have to pass your actual output in the training data, and also you have to pass the predicted output on the training data. Now calculate the mean square error. So I'm getting the almost 0, you can see almost 0. So I'm very happy. So I'm very happy with the training error and also with the testing error. Almost both are equal to 0. So now I'm trying to deploy my model. So how we deploy the model? Simply, I am taking these small things I am explaining. Like that, you can deploy your model in the web application. Like that, you can deploy your model into the mobile application also. So deploy the model is nothing but the using the updated weights and the bias parameters. That's it. So this application is, I want to ask the user enter the A value, enter the B value, enter the C value. So whatever the inputs are coming, that will be multiplied with your updated weights and add the updated bias parameter. It will give the net input to your output layer. Once you got the input, how we get the prediction? Output of the output layer. That is because I'm using the sigmoid activation function, 1 by 1 plus minus input. So 1 by 1 plus exponential of minus input minus z. That will be the prediction. So if you want, you can deploy the model and see it. We will check with any one of this parameter. Can I go with this part or this part or any part? You can go. I want to take this part 0.5, 0.6, 0.7. I'm expecting the output 0.8. So first value is 0.5. Next value is 0.6. Next value is 0.7. My expectation is 0.8. Yes, this is the 0.8. Right? How it will go in? Because your neural network model already trained. Your ANN model already trained. So once it is already trained, so that it will give the output. So if these are the inputs, your output will be 0.8. If these are the inputs, your output will be 0%. You can try 0.6, 0.7, and 0.8. We will try with one more case study. So 0.6, 0.7, and 0.8. So I'm getting the 0.7 here. Yeah, this is the 0.71. So this is also 0.71. Because your model is already trained. So that if you give these are the inputs, you will get the what will be the proper output that will be gives. Because already trained. So that application performing well now. So this is how the implementation of the ANN model with the input layer, output layer, weights, bias parameter, and with nonlinear activation function. Okay, this is the slowly we are building the complexity of the ANN model. I can go directly, but you have to understand how it will work in the back end. That's why I'm going slowly a step-by-step process. Now, actually, as I said earlier, in a real time, in a practical examples, it's a very, very highly complex. Your output and inputs are not direct relation, very highly complex, highly non-linear relation. In that case, a simple models with only single input layer with single output layer, you won't get the better results. So you have to increase the complexity of your model further by adding some more layers in between your input and output. The layers which are used between the input and output are called as the hidden layers. Why it is called the hidden layers? Because these layers are hidden by your input and output. Input layer we're giving the inputs, that is visible. For output layer we're taking the output, that is also visible. But what are the layers in between that is not visible? Those layers are not visible, so that layers are called as the hidden layers. Understood? So in practical cases, in the real time, in real-time examples, in real-time problems where there is a very high complex relation between the inputs and outputs will exist, in such scenario, you can't work well with the simple one input layer and output layer. You have to add the multiple layers in between. That's why it's called the deep neural network model. So deep neural network model means in between input and output, the number of hidden layers will be increases. That is called the deep neural network model. Okay, so in the real-time problem, we must use, it may be a computer vision problem, or it may be NLP related problems, or it may be a real-time temperature humidity predictions, where there is a high complex relation between the your inputs and outputs. In such scenario, simple ANN models with single input layer and output layer, it won't work. You must go beyond that. You have to increase the complexity by adding the few more layers between your input and output. Between your input and output. Okay. Now that part we will discuss. Okay. I hope you understand till now. Now we will move to the during the delivery of the session at any point of time. If you have any questions, you can use chat box or you can unmute yourself. You can ask. So I will explain. Now I want to increase the complexity of the model. So previously, so let's assume if you are A, B, C, and X. So this is my data set having the 3 input features and 1 target variable. I have some data, some few thousands of samples are available. Let us assume many data samples are available to train the ANN model. But there is a complexity. There's a complex relation between my target variable and the input features. Simple input layer and output layer will not work. Okay. So I want to increase the complexity of my ANN model. So as usual, your ANN model contains the input layer and output layer. So my input layer contains 3 neurons. So let us assume I want to build the one ANN model. So I want to build the ANN model. So to predict the to predict the output. So I can take it as O other bed. So to predict the, sorry, it is a desired output. I can call it as a desired output. To predict some output O based on the inputs A and the input B and input C. So because there are the three inputs, so I want to use the three neurons in the input layer. This is the neuron 1 and neuron 2 and neuron 3. Three neurons in the input layer. So this layer is called as the input layer IP. This neuron is called the input layer. And because in the output side, you have the only one variable you are going to predict. You are predicting the only one variable. So that here you have the only one neuron in the output layer. In the output layer, you have the only one neuron. Okay. So this is called as input layer. It is a visible, which is connected to the input features. This is called as output layer. It is also visible, which is connected to the output, from where we are taking the output. There's a one more layer between your input and output that is called as the hidden layer. So these hidden layer, you have the some neurons like input layer and output layer. You have the some neurons in the hidden layer also. But the number of neurons in the hidden layer, it is like a hyperparameter. You can't tell only these number of neurons will be there in the hidden layer. That is you have to tune it. You have to randomly tune it. So as of now, I want to consider the 1, 2, 3, 4, 5 neurons in the hidden layer. So this is called as my hidden layer, HL. So this is my input layer, this is the output layer, this is called as hidden layer because this layer is hidden between your input and output. Right? Hope you understand. Now, so all the neurons of the input layer are connected to the output layer. Neurons of the input layers are input neurons are connected to the hidden neurons. So like this, we are connecting everything. Like this, we are connecting everything. And similarly, hidden layer neurons are connected to my output layer neuron. So this is called as a fully connected. So this is called as a fully connected. Okay, so this is the, I'm increasing the complexity of the ANN model. I'm increasing the complexity of the ANN model. So here in the input layer, so we have the three neurons. That's the fixed because we have the three input features. And this is my output layer where I have the only one neuron because I have the only one variable to predict. In between hidden layer, the number of neurons in the hidden layer, you can't tell. So it is the hyperparameter. You have to change it until you got the better model, better performance. Okay, hope you understand, right? So now you can see the architecture of the model will be slowly increased. Architecture of the model is slowly increased, right? So I think everyone is following, right? So now see, so every connection has some weight, right? Every connection has some weight, right? So the weights between the weight matrix between the input layer and hidden layer, to call this one as a Wij. Your choice. I am using the I layer as a input layer, J layer as a hidden layer, K layer as a output layer. So between the ith layer and jth layer, the weights are called as the Wij. How Wij looks like? Wij looks like, see, 1, 1. First neuron. So I can call it as the W11. First neuron, second neuron, I can call it as a W12. First neuron, third neuron, I can call it as a W13. First neuron and fourth neuron, I can call it as W14. First neuron and fifth neuron, I can call it as a W15. So like that, W21, W22, W23, W24, W25. Again, W31, W32, W33, W34, and W35. This is my size of my weight matrix between the input and hidden layer. The size of the weight matrix equal to 3 cross 5. This 3 represents the number of neurons in the input layer. This 5 represents the number of neurons in the hidden layer. So this is my size of the weight matrix. You have to remember everything. Maybe I will ask how many number of, what the size of the weight matrix between the input and out hidden layer. Then you have to tell, you are in a position to tell these are the shape or size of the matrix. Similarly, if you go to between the hidden layer and output layer, between jth layer and kth layer, so this weight matrix I am calling as a WJK. I am calling it as a WJK. Like I want to call WJK is like a hidden layer 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. That means one neuron. Second neuron, first neuron. Third neuron, first neuron. Fourth neuron, first neuron. Fifth neuron, first neuron. So you can write WJK as W11, W21, W31, W41, W51. Like that you can write. Fine. So now, so it's clear, right? Like that you have the WJ. Here, as of now, I'm not considering the bias parameters. I will add the bias parameters later. Slowly, I hope everyone follow, because my intention is to make you understand. That's why I'm taking the, from the basics, I am moving slowly. Okay. Now, so this is my architecture. I'm not taking any bias parameter. So I hope everyone is in online. So now you have to tell me what will be my step 1. Everyone, anyone can respond. What will be my first step in the training algorithm? To train my model, this ANN model, what will be the first step? So can you please respond? So if you not respond, means it's not creating any interest. That's why I'm asking again. So what will be the first step? Is someone responding? So at least some person is there listening my class. I have some that confidence. So what may be the first step during the training algorithm? I want to train this model. I have a data. ABCX data is available. I want to train this ANN model using the back propagation algorithm. What I have to do?
Hello, sir. You have to first read the data.
Right. So thank you very much, sir. So read the data. So we have to read data. The data is A, B, C, and X. Next, sir.
Next, you have to set the control parameters.
Okay, sir. You can set a learning rate as a 0.1. I will took a number of epochs as some 100 like that I take. Okay, next.
Okay, so then you have to randomly assign the weight.
Right, sir. Perfect. So we have to randomly initialize. What we are going to random initialize, sir, here in the model? What we are going to random initialize? Which matters?
Weight matrix.
Sir, weight matrix. That is the Wij matrix. That is the these values we have to choose randomly, and Wjk. This weight matrix also here available. That also we have to choose randomly. That's it, sir. Perfect. So because as of now I'm
So
not
that
getting
is
the
a matrix, or WJK is a matrix, or?
yes, sir. Wij and Wjk are the matrices, sir. Weight matrix. This will be like this only. For example, random values are, let us assume, for example, I will take very simple. This is the input.
Sir, my question is like our output is only one, right?
Right, sir. One only.
So, okay, so
No
it
problem,
will
sir. You
be
can ask, sir.
so
Whatever
it will
doubt
be
you have, please.
vector,
Sir?
or so that last second weight matrix is a vector or a matrix?
You can call it as a vector, or you can call it as a matrix of column matrix like this.
Yeah, yeah. Okay,
Because
sir,
we have the only single element.
yes, sir, yes, sir.
Right, sir. Okay. So I can call it as a vector, or I can call it as a matrix with a size of 5, 1, 5 rows and 1 column matrix. So we have to randomly initialize all these values. Whatever the values we have, 5 into 3, these 15 values, and these 5 values initialize randomly at the starting. That is the first step. Nice, sir. Thank you very much. Now, what is the next step, sir? Anyone? Sir, team. So what will be the next step? Now we read the data, we initialize the weights, and we initialize the everything. What next, sir? So remaining participants also, if you respond, otherwise it's a waste, right? Because you are paying something, you are listening the class, I hope to learn something, right? So that's why you have to follow. Sir, what will be the next step, anyone? So we are reading the data. Next step is we have to set our iteration 1. Step 3, we have to take the first sample. Now, what will be the step 4, sir? What will be the step 4? Same, sir. From yesterday onwards, I'm following the same concept, but slowly I'm increasing the complexity. So once you understand the previous sessions, then easily understand this part also. So what may be the 4th step? Can use chat box also. Yeah, randomly initializing. Thank you, Munalini. Randomly initialize the weights, set the iterations. Very good. Thank you very much. So what will be the next step? I can check the so anyone, what will be the next step? We initialize the random initialize the weights, and we read the data. So and we set the first iteration, we set the first sample. So what may be the next thing? What we have to do next? Anyone? It's it's okay. But if you respond, it's very good for me, but it's okay, fine. No issue, I will explain. So next what we have to do, that is, next step is we have to calculate our prediction. We have to calculate this prediction we have to calculate. But if you want to calculate this output, first we have to calculate the input to your output layer. If you want the input to your output layer, you have to know the output of the hidden layer. If you want the output of the hidden layer, first you have to know the input of the hidden layer. Okay. Now tell me, let assume jth layer, right? I am calling net j. So that is called as the input of the jth layer or hidden layer. How I calculate the net j? Anyone? How we can calculate the net j? Net input to this hidden layer or jth layer. How we can calculate? How we can calculate this net j? Net input to this hidden layer. How we can calculate the net input to this hidden layer?
So it is Wij.
Perfect, sir. Right. So we have to multiply Wij with, so let us assume our inputs. Right, sir? So we have to multiply with our inputs. So that will give the net input to your hidden layer. Now tell me, if this is the net j, what is the Oj value? Actually, we want the output. Output of the hidden layer is going to the output layer. Output of the hidden layers are going to the output layer. So what is the output of the hidden layer Oj? Assume I am taking the linear activation function in the hidden layer. Then Oj equal to Oj, nothing but the, so this is the input, sir. These are the inputs to your hidden layers. That will be calculated based on the multiplication of your Wij with your inputs. It will give the net input to the hidden layer. But the output of the hidden layer going to the output layer, right? So what is the output of the hidden layer if you are using the linear activation function?
So again, you have to multiply by Wjk transpose.
Not required, sir. So because it is a linear activation function, right? So linear activation function means whatever the input, the same thing will be the output. Yesterday we discussed the linear activation function. So Oj equal to simply net j. Oj equal to net j because I'm using the linear activation function. Okay, fine. So once you got the Oj value, that is the output of the hidden layer. These output of the hidden layer passing to the output layer through the Wjk matrix. Now I'm asking, what will be the net input to you output layer k? Net k, nothing but net input to your output layer k. So what will be the net k, sir? Anyone? Net k, nothing but net input to this output layer, kth layer. That's equal to
Net j times Wjk.
right, sir. Net j or Oj, because in our case both are same. So I can call it as a Oj or net j, both are same. So net j times of Wjk. There is a matrix multiplication between these two, and here also matrix multiplication between these two. That is the net k. Now, if the net k is nothing but the net input to your output layer, and assume that here also I am using the linear activation function, then what will be the my OK or output? OK or output. Output equal to So what is the output of our output layer? The total input to my output layer equal to this part you already told. So I am using the linear activation function in this neuron. Then what will be the output of the output layer? Because I am using the linear activation function, whatever the input to the neuron, the same will be coming out as the output. So OK equal to, can you call it as a net K? So this is my forward propagation. So this is the forward propagation where we are calculating the output OK in the forward propagation. In the backward propagation, we are updating the weights. In the backward propagation, we are updating the weights. Now, how we will update the weight, that we will discuss now. It's important. Now, after calculating the OK, I don't want to go for the step 5. Before that one, I want to go for some mathematical derivations. Now tell me, so we got OK, right? We got output, actual output. Sorry, we got predicted output, right? Now after calculating the predicted output, what we are going to do? So after calculating the predicted output, what we are going to do? After calculating the OK, what we have to do? Anyone? Anyone? I'm calculating the forward propagation completed. Finally got the predicted output. But in the backward propagation, I am going to update the weights. If I want to update the weights, that means delta Wij, delta Wjk. If I want the delta Wij and delta Wjk, first what I have to calculate? Anyone? So we have some people who can respond whether it is right or wrong. We are learning here, right? So if what you feel, forward propagation completed, we are calculating the predicted output. What we have to do next? No, it's a very simple, right? What we did earlier, after getting the output of any ANN model, what you are calculated next? What we calculated after calculating the output of the neural network model, ANN model. After finding the predicted output of a neural network model, what we calculated? What you found? Anyone responded in the chat box? I will see others. So you can use either chat box or anyone? Predictions are completed. So after that, what we have to do? Okay, anyhow, so it is a delaying. So that's why I'm moving forward. So when I'm asking if you respond, that should be very interesting for me. Okay, fine. So after calculating the okay, all the things. So now you have to calculate the error. How we calculate the error? Error equal to 1/2 times of your desired output dk. That is the actual output coming from the data set. Fourth last column dk minus your predicted output OK whole square. So this is my error. Now based on this error, we are trying to update Wij, Wjk such that I am trying to minimize this error function. I'm trying to minimize this error function. I want to minimize this error function. To minimize this error, I have to update the Wij and Wjk. Now we are going to the gradient descent optimization. As per the gradient descent optimization, anyone can at least tell me how I can calculate change in weights for the Wjk. That means change in weights for the weights connected between my hidden layer and output layer. How I can calculate delta Wjk? What is the formula based on our gradient descent algorithm? At least, please respond. How we can calculate the delta Wjk based on our gradient descent algorithm? The step I am expecting. Please respond fast if possible. No. Okay. So delta WJK equal to minus eta into dou E by dou WJK. Now, how we can calculate this one? Minus eta dou E by dou WJK can be written as dou E by dou OK and dou OK by dou WJK. That's equal to minus eta dou E by dou OK. So differentiation of this error function with respect to OK, 2 come forward, 2 to cancel. So you have the dk minus OK. Because OK coefficient is minus 1, so it will become a plus. Next one is a dou OK by dou WJK. OK expression, where is the OK expression? This is the OK, right? OK is nothing but the net K. Net K is nothing but the net J into WJK. So when you are differentiating, see from here you can see OK equal to net K. So OK equal to net K means net J into WJK. Net J into WJK. Right? So here again, net J is nothing but the OJ, right? So you can write, so you can keep like this only, no problem. So dou OK by dou WJK. What is the dou OK by dou WJK? Nothing but the net J. Nothing but the net J. So understood that there's nothing but the net J. So that is the expression for the delta WJK. So delta WJK is equal to delta WJK equal to eta into dk minus OK. OK can be called as the net input to the kth layer. Net input to the kth layer multiplied by net input to the jth layer, net J. So this is the expression for the delta WJK. This expression we need to remember while writing the coding part. Right? So what will be the next step? So delta Wij, that's equal to minus eta into dou E by dou Wij. Now, how we can do this part? You can see how we can do this part. So that is the minus eta into dou E by dou Wg further converted as splitting the partial fractions dou E by dou OK, dou OK by dou OK by dou, how we can write dou OK by dou OK by dou net J and dou net J by dou Wij. If I do this one, I'm getting the same expression, right? Minus eta. So this one cancel, this one cancel, dou E by dou Wij only. Both are same. Okay. Now, minus eta dou E by dou OK. Dou E by dou OK means differentiate this expression with respect to the OK. These two come forward, 2 to cancel. OK coefficient is minus 1, so it will become plus. So here you have the dk minus OK into dou OK by dou net J. Dou OK by dou net J here. So what the expression we are getting? Dou OK, differentiate OK with respect to net J. Then you will get the WJK. Later, dou net J by dou Wij. Dou net J, this is the dou net J, this is the dou net J, dou net J by dou net J by dou Wij. Dou Wij. So what is the output? Dou net J, differentiate net J with respect to delta Wij, then you have the A, B, C. So simply you have to multiply with A, B, and C. So this is the my final expression delta Wij equal to eta into dk minus OK is nothing but the net K, because we are using the linear activation function. That's what I'm saying. Multiplied by WJK, multiplied by WJK, and multiplied by your inputs A, B, C input features. So this is the expression for the delta Wij. This is the expression for the delta WJK. So you need to remember these two expressions while writing the algorithm. Now coming to the algorithm part. So we calculated output. Okay. Then what we have to do? Step number 5. We have to calculate the delta W. We have to calculate delta W. So delta W equal to delta W means there are the two weights. It is not a single weight. We have the two weights. So two weights means one is delta WJK. How we can calculate the delta WJK? Just now we derived. So delta WJK can be calculated as eta into dk minus net k, that is the net input to the kth layer, into net j, net input to the jth layer. So you can write eta into dk minus net k and multiplied by net j. Similarly, delta wij, that's equal to, how we can calculate delta wij here? Eta into dk minus net k into wjk into inputs, right? So that's what I'm writing here again. So eta into dk minus net k multiplied by wjk multiplied by your inputs, multiplied by your inputs A, B, C. These two expressions already derived. So from the derivation, I am including the step number 5. So rest part is you are able to understand. At least you can respond now. What may be the step number 6? We are updating, we are calculating the change in weights for the both layers, between the input and output, and also between the hidden and output layer. So what is the step number 6? What will be the step number 6 now? Anyone? What will be the step number 6? So what will be the step number 6? After calculating the change in weights between the input layer and hidden layer, and change in weights between the hidden layer and output layer, so what we are going to calculate? So next step is we have to calculate, update the weights. Wij equal to Wij plus delta Wij. Similarly, calculate Wjk equal to Wjk plus delta Wjk. We have to update the weights. So after updating the weights, we move to the step number 7. So step number 7 is we are updating the sample equal to sample plus 1. And we move to the step number 8. What is the step number 8? Here we are checking whether all the samples in a training data completed or not. Sample is greater than ns, number of samples in a training data. If it is a true or if it is a false. If it is a true, that means your current sample number is more than the number of samples in a data set. That means you covered all the data samples available in the training data. Then you move to the next step. If it is a false, then you have to move to which step? You have to move to step number 4. You have to move to step number 4. So next step is, what is the next step? Step number 9. So next step number 9 is after completing all the samples, you have to update your iteration count, iter equal to iter plus 1. And step number 10 is you have to check whether your current iteration value is greater than number of epochs or maximum number of iterations you mentioned reached or not. If it is a true or if it is a false. If it is a true, go to the next step. If it is a false, again you are starting the new iteration, again starting from the first sample. So first sample means you have to move to the step number 3. So after going to step number 3, now move to the step number 11. Next step is step number 11. What you have to do here? You have to save model parameters. So model parameters saving nothing but the save your weights and calculate training error and testing error. Calculate training error and testing error. So after that, if you and your client are happy with the training error and testing errors, then simply deploy your ANN model in application backend. In the application backend, you have to deploy your ANN model, and then you have to stop your complete process. So this is the complete algorithm for the ANN model with the hidden layer with the linear activation functions. Right? So now we are trying to implement this part. implement this part. That means I want to build one small ANN model with one input layer, one hidden layer, one output layer, and I want to take in the linear activation function. Now I have to take the data, I have to split the data, I have to train my model, I have to calculate test errors, I have to calculate the train errors. If both are happy, that means training error and testing errors are very less, and myself, my client also very happy, then simply deploy that model. Simply deploy that model. Okay, so I hope you understand this mathematical part and the complete derivation. Otherwise, I will draw the flow chart also. After drawing the flow chart, I will move to the implementation part. After drawing the flow chart, I will move to the implementation part. Okay. So start your flow chart, and as per our algorithm, you have to read data. The data may contains input features A, B, C, and your output X, and also randomly initialize your weights Wij and Wjk. You have to randomly initialize, and also set the learning rate value as a 0.1, and also you can set number of epochs equal to 100 like this, for example. So this is the initialization part. This is the initialization part. Okay. This is the initialization part. So after initialization, what we have to do? We have to calculate. So after initialization, we have to calculate our outputs. How we calculate outputs? First, you calculate the net input to the your jth layer, nothing but a hidden layer. That's equal to Wij, that is the weights between the input layer and hidden layer, multiplied with your input features A, B, C. So that is by net j. Because I am using the linear actor function, your net j is nothing but the Oj. So I don't want to mention separately. Your output of the hidden layer is nothing but the input of the hidden layer, because I am using the linear activation function. So after that, we have to calculate the net input to your output layer. So net input to the output layer is nothing but the output of the hidden layer going to the your output layer. Output of the hidden layer going to the output layer. So what are the inputs? Your inputs are the outputs of your hidden layer. So how we can calculate the input of the output layer? So that's equal to Wjk, that is the weights between the hidden layer and output layer, multiplied by inputs are coming from the hidden layer. So that's why you can write it as a net j or nothing but the Oj. So you have to calculate this is your OK or output, because I'm using the linear activation function. I'm using the linear activation function, whatever the input, that is the output. Both jth layer, in both jth layer and in the kth layer, I am using the linear activation function. So net j equal to Oj, net k equal to OK. Okay. Now, so up to here it's right. Okay, fine, right? So after predictions, what we have to do? So after doing the predictions, we have to do with so initially set your iteration count equal to 1 and the sample count also equal to 1. Now after calculating the net, that means predictions of a ANN model, now calculate the delta Wij or Wjk, and also calculate the delta Wij. How we can calculate the delta Wjk? How we can calculate the delta Wjk? So delta Wjk is equal to eta into dk minus net k, because I'm using the linear activation function. Anything else? I think dk minus net k, and multiplied with we derived, right? Just now we derived. So delta Wjk equal to dk minus net k into net j and Wij equal to eta into dk minus net k into Wjk multiplied by your features A, B, and C. I think it's same. Right? Eta into dk minus net k, Wjk into ABC. That's it. So we are calculating the delta Wjk and delta Wij. So after that, we are going to update your weights. That means Wij equal to Wij plus delta Wij, and Wjk equal to Wjk plus delta Wjk. So once this is completed, that means weights are updated. Next, what we have to do? Update your sample number. So sample equal to sample plus 1. So what next? Once the sample count is updated, now check whether your current sample number is greater than number of samples available in the training data or not. If it is yes, move to the next step. Otherwise, we have to move to where if the number of samples are not covered, it is a false. Then move to the fourth step. Fourth step is nothing but the net J calculation. Nothing but the net K calculation. Okay, that means where to move now? From here to net K calculation, here we have to move. Suppose if it is a true, if it is yes, then what we have to do? Now we are going to update your iteration count. So iter equal to iter plus 1. Now again, update your samples. So not sample, iter. Iter is greater than number of epochs or not. If it is yes, go to the next step. If it is no, where to go? If the number of iterations are not reach the maximum number of epochs, the number of iterations not reach the maximum number of epochs false, then go to the step number 3. Step number 3 means again start with the first sample. Again start with the first sample. So for that purpose, it's better not to use sample here. You can keep a small box here. So here it is sample equal to 1. Now, if the iterations are not completed, move this box to move to here. Again, go to the first sample and do the calculations. If it is a true, simply, as I said earlier, just save model. That means save the weights and bias parameters. And what next? Calculate errors. And if the errors are less, simply deploy model. And you can stop the algorithm. So this is my complete flow chart for this case. So this is our complete flow chart in case of the ANN model with a linear activation function by considering the input layer, hidden layer, and also output layer. Right? Now we are trying to implement this part. Later we will take a break. So first we will implement this part and later we will take a break. Okay. So coming to the implementation part. ANN with hidden layer with linear activate function, but no bias. That's what we understood till now we discussed it. So this is the data. I have the 3 input features A, B, C. The values are like this, and the corresponding output values are stored in the X. Corresponding output values are stored in the X. This data also available in my Google Drive. So just I'm trying to import the data. So these all things we know. That's why I will move further fast. Okay. So I want to read the data where this data is available in my Google Drive in the NNDL data folder. The sample data 03 is the data, the same data. So simply run this code. So this is the complete data. That data is stored with a variable called data variable. Whatever the data is available in this Excel file, that will be read, that will be extracted and stored in this variable data. This is the content. So next step is we know data split. Next step is we know there is a data split. We know all the things. That's why moving further. Simply I'm trying to split the data using train_test_split method. I want to split the data for the training purpose and also for the testing purpose with 5% of data in the testing. So after data split, again, we have to randomly initialize the weights. What are the weights here? We have Wij and Wjk. So you can see the code. So random initialization, Wij, Wjk. Just I consider the np.random.uniform. My lower limit is -1, upper limit is +1. -1 and +1. You can get any value. You can randomly pick any value between the -1 and +1, assign it as a weight matrix. But please, anyone following, please tell me why I'm taking here 3,5, why I'm taking here 5,1. Anyone, please? I will wait for 1 minute. Why it is a 3,5 and why it is a 5,1 in case of the Wij and Wjk? Any idea? Because it is a 3,5, because you can see our matrix. So you can see our architecture. If you see our architecture, so this is my Wij, 3 rows and 5 columns. Because 3 input neurons, Wij is between the input layer and hidden layer. Input layer has a 3 neurons, so 3 rows. hidden layer has the 5 neurons, so 5 columns, so 3 cross 5. That's why it is a 3 cross 5. Coming to the WJK, that is between the hidden layer and output layer. That is between the hidden layer and output layer. So hidden layer has the 5 neurons, so 5 rows, and output layer has the only 1 neuron, so 1 column. So that's why 5 comma 1. That's how we are randomly initialize the weight matrix Wij and Wjk. So after initializing the Wij, Wjk, what is the next step? Forward pass. Forward pass means we are trying to calculate the predictions of a ANN model. So this is the forward pass. So see the code for the forward pass. Just simply I'm taking a small function. For the forward pass, I'm taking the small function. I don't want to write the complete code again and again. I will create a small function and I will call the function for the forward pass rather than all the lines. So how we create a function in the Python, that the syntax is you have to use DEF. That means you are defining a function. What is the name of the function? Forward pass. And what it is expecting, you have to pass your data. You have to pass your Wij matrix. You have to pass your Wjk matrix. And you have to pass your sample number, which sample you are passing. Because we pass first sample, calculate the prediction. Pass the second sample, pass the prediction. Pass the third sample, calculate the prediction. So J is the sample number, where A is your data set, training data. Where Wij, Wjk are called as your weight matrices. Wij and Wjk are called as the weight matrices. So inside the function, what we have to do? How we calculate the Oj? How we calculate the OK? Oj is nothing but the net J. OK, nothing but the net K. OK is nothing but the net K. Oj nothing but the net J. How we calculate the net J? Net J equal to or Oj equal to the matrix multiplication of Wij and input features. It is the matrix multiplication of weight matrix and your input features. That is called as the Oj or net J. So Oj equal to matrix multiplication of your input features. A is your data. Here you have to pass your data. In that data, you have to choose the first 3 columns because these are the features A, B, C. Multiply those ABC values with the Wij matrix. Wij matrix. That will give the net J nothing but the Oj. Right? Again, now OK I want. If I want to calculate the OK, how we can calculate the OK? OK is nothing but the net K. Net K nothing but the net J. Net J nothing but the Oj. That means Oj into Wjk. You can see Oj into Wjk. That will give the output. So just simply return your output of the hidden layer and output of the kth layer, nothing but the output layer. So this is your forward pass. In the forward pass, we are calculating the output of the hidden layer and also output of the output layer. Everyone following, at any moment of time, if you don't understand, please let me know. Next, coming to the backward pass. So in the backward pass, what we are doing is slightly complex, but same thing I'm implementing. When coming to the programming, we have to write the logics, right? This thing only I am trying to implement. Only this part only I am trying to implement. Sorry. Yeah, backward pass means delta Wjk, delta Wij, right? These 2 equations I want to implement, but the code is slightly complex. So now for the backward pass, I am creating one function, define a function with the name of weights, updation, back propagation. You have to pass your data set. You have to pass your learning rate because I am using the eta learning rate. And you have to pass Oj and OK. Why? In the expression you can see dk minus net k, nothing but the OK, net j, nothing but Oj. So you require the dk, you require the OK, you require the Oj. So Oj, OK, you require. In addition to that, you have to pass the Wij, Wjk also because you require that also, Wjk. So pass the Wij, Wjk also. Now J is called as a sample number. So pass the first sample, update the weights, pass the second sample, update the weight. That's what we have to do. Now how we calculate the delta Wij? I'm initializing the delta Wij with all zeros. See, delta Wij, what the size of the delta Wij? Delta Wij. If you want to add delta Wij to the Wij matrix, want to add the delta Wij to the Wij matrix. Wij matrix size we know. It is a 3 cross 5. So definitely if you want to add something, your delta Wij should be 3 cross 5 matrix. That 3 cross 5 matrix I was initialized with zeros first. Later I will update. The 3 cross 5 initialize zeros initially. Later I will update. Okay. Next, we have to calculate the, as per our flow chart, as per our algorithm, we have to calculate delta Wjk equal to eta minus dk minus ok into oj. That's what we have. Delta Wjk equal to learning rate eta multiplied by desired output. Desired output is available in a data set in the last column. So that is the E of j in the last column. That means third index column. 0th index column, index 1 column, index 2 column. These three are the inputs. Third index column is called as your output. That's why I'm taking the actual output here. And this is the actual output minus your prediction, OK. That is the dk minus OK into net j. Net j nothing but the oj. So that is the oj. So this is how I am calculating the change in weight matrix. Change in weight matrix eta into dk minus OK into oj. Okay. Now I'm trying to update. So Wjk equal to Wjk plus delta Wjk. For the dimensions mapping, I'm calculating the transpose. I'm calculating the transpose. That's simply Wjk equal to Wjk plus delta Wjk. Next step is we have to calculate the delta Wij. How we can calculate the delta Wij? So delta Wij will be calculated. Delta Wij will be calculated for every neuron. So I want to tell one thing here. If you observe this architecture, this part I am trying to concentrate now. So 3 inputs, right? And here you have the 5 hidden layers, right? Now for every neuron, you have to calculate the delta W of this one, delta W this one, delta W this one. Then those delta W values you have to keep like this. Similarly, for this one also delta W calculate, delta W calculate, delta W calculate. Change in weight for this path. That value is also included here. Similarly, for the third neurons, delta W calculate, delta W calculate, delta W calculate. That 3 values you have to keep it here. And this also delta W calculate, this W calculate, delta W calculate, and keep here. And last one also you have to calculate delta W, and delta W keep here. So this is your delta Wij matrix. Delta Wij matrix, while writing the code, you have to do it for the every neuron. Every neuron gives the 1 column. Every neuron gives the 1 column because this neuron 3 values, that is the 1 column. This neuron 3 values, that is the another column. This neuron is 3 values, again third column. Fourth neuron has the 3 values, that is the fourth column. Fifth neuron has the 3 values, that is the fifth column. So this matrix we have to find delta Wij. That's what I'm doing here. Delta Wij, whatever the neuron consider, that column only I'm updating. In the delta Wij matrix, first neuron, first column, second neuron, second column, third neuron, third column, like this updated. That's why delta Wij, k means k equal to 1 means first neuron, first column. K equal to 2 means second neuron, second column. Why I'm taking the 5 here? If anyone following, tell me why I'm taking the 5 here. Why I'm taking the 5 here? Please respond. Why I'm taking the 5? No? It's very simple. Maybe no one is following. Just I am shouting because I'm taking some registration fee and it's my responsibility to deliver. But departments also some responsibility to learn and to listen. So because it is taking the 5, because in my hidden layer I have the 5 neurons. In my hidden layer I have the 5 neurons. Okay. Now we have to update the delta Wij matrix. How we calculate the delta Wij? Eta into, so this is the eta, dk minus ok. D means from the data set third index column minus ok into delta Wjk and your ABC. ABC is nothing but the inputs from the 0th index column, index 1 column, index 2 column. This is the ABC. Then you got the delta Wij. After that, it is simple. Wij equal to Wij plus delta Wij. Here we already calculated Wjk equal to Wjk plus delta Wjk. So like that, we are updating our weights. Simply run this cell, this complete cell for the backward pass. This is the forward pass. These two cells completely called as the back propagation algorithm. In the forward pass, we are calculating the outputs or predictions. In the backward pass, we are updating the weights. That's what's called a back propagation algorithm. So after calculating the updated weights, these are the functions only. I will use these functions inside the training algorithm. Otherwise, I have to write the complete code in the training algorithm. Instead of that one, I want to call only these functions. Now you can see this part. Now I am setting the learning rate as a 0.001. As usual, we know from the flow chart how many for loops are there. 2 for loops, outer for loop for the iteration, inner for loop for the sample. So outer for loop for the iteration. So you can call EPO epoch equal to 100, and you can call here epochs. There are the 100 epochs. And this is the outer for loop is for the number of iterations, and inner for loop for the samples in the training data. After that, what you have to do? You have to find the predictions, right? In the inside, you have to calculate the predictions. So predictions is based on the forward pass function. The forward pass function, you have to pass the training data, you have to pass the Wij, you have to pass the Wjk, you have to pass the sample number. After calculating the predictions, you have to calculate the change in weights, and later you have to update the weights. That will be coming from calculating the change in weight, updating the weights, calculating the change in weight and updating the weights coming from your backward pass. So instead I am using the backward pass function. This backward pass function also required your A, nothing but the training data, learning rate, you require OJ, you require OK, you require Wij, you require Wjk, and the sample number. So this process will be repeated until you are reaching the 100 epochs. This is, so initially, my initial weights are like this. You can see 0.50516, but my final weight is 0.65 something. Right? So weights are updated for the 100 epochs of training process. So rest of things are same. So once the training was completed, what you have to do? You have to calculate the output predictions based on the test data and compare these predictions with the actual output and calculate the error. Similarly, do the predictions on the training data and calculate the compare the predictions on the training data with the actual output values in the training data and calculate the error. So that is the motto. So this is all things we know already. So output of the prediction with the test data. So test data, if you want the predictions, which function we can use? We have the two functions. One is the backward pass, another is the forward pass. In the forward pass, we can get the predictions. So to calculate the predictions, I am using the forward pass. For the forward pass, if you want the test prediction, pass the test data. You have to pass the updated weights, and also you have to pass your sample number. For every sample number, it will give the predictions. Prediction nothing but OK, right? Actually, this forward pass gives the two values. One is the OK, another is the OJ. But we are much concentrating on the OK. That is nothing but the OK is nothing but the output of the neuron. You can see output of the ANN model. OK is nothing but the output of the ANN model. This is what we required for the training error or testing error. Final output is required. That's why I'm taking only OK value, not OJ value. That is the reason why there is some dash here. That means I'm not taking the OJ. I am taking the only OK, and that OK value stored here. This is the predictions on the test data. So if you want to see the value, remove this shape and you can print here. So this is my predicted output on my test data. Similarly, do it for the train data also. Same thing. Only thing is, instead of Q2, I am passing the Q1 because Q2 here test data, Q1 here train data samples. Remaining all are same. If you want to see the predictions with the training data, simply remove this shape and you can run again. These are the predictions on the training data. So once the predictions are completed, you can easily calculate the test mean square error, training mean square error by passing the mean square error function with the test data, actual output, and predictions with the test data. Similarly, for the training error, pass the training data actual output available in the last column and pass the training data predictions. Then it will give the mean square error. So you can see the mean square error is almost equal to 0. I am happy. So then I am trying to deploy the model. Deploy the model means you have to use updated weights Wij and Wjk and calculate the predictions. So you can see this prediction. Again, same process. You will ask the user enter the A value, B value, and C value. And all the three values are stored in a vector called input vector. That input vector you have to pass, and you have to use the delta Wij, you have to pass Wjk, because there was only one sample, right? Sample 1 means 0th index. That's why I'm passing the only 0 directly. Because I had only one input, A value, B value, C value as a single row. That means only one row, that's the index 0. That's why I'm keeping the index 0 here. Hope, right? So simply run this one. It will ask something. We will check with any of the already available data. I want to go with 0.21, 0.2, 0.3. I'm expecting 0.73. So 0.1, 0.2, and 0.3. So I'm getting the, actually, my actual value is 0.73. My model is predicting 0.70, somewhat close to. So that is our goal, right? Every training algorithm goal is trying to update the weights Wij, Wjk in such a way that your predicted output close to your actual output. That the 0.73 is the 0.1 close to each other. That's fine. Okay, that's how we will work with the ANN model without with the linear activation functions with the multiple layers, with hidden layer, with input layer, and with output layer. So this is the session for the day 3 first session. And now we will take a break for the 15 minutes.